In this complementary video, we will describe the concepts used by our method to produce complex multi-contact animations such as these. To illustrate our approach, we will consider the simple example of this humanoid character. In this initial phase, both feet are in contact as well as the right hand. To reach this goal phase, the character has to move its right leg from the back platform to the front one. In the process, it will thus break a contact and create a new one. We consider the issue of automatically computing a collision-free animation that will achieve this motion. In the scenarios we consider, the contacts created are not coplanar and the locomotion is not gated. This results in non-trivial kinematic and dynamic constraints that must be satisfied to produce plausible results. To reduce the dimensionality of the problem, we express these constraints as the center of mass, or COM, of the character. A sampling-based scheme is used to compute this green polytope. It represents the kinematic constraints that apply on the COM when the left foot is at the displayed position. We can compute similar polytopes for the right foot and for the right hand. Under a hypothesis of independence, the intersection of the polytopes corresponding to each active contact gives us the kinematic constraints of the center of mass of the character. For COM positions that lie in the polytope, we can find whole body configurations that satisfy the contact constraints. However, because we do not account for dynamic constraints, they may look unnatural, as illustrated here. The introduction of such constraints results in a non-convex problem extremely hard to solve. Thus, in a first step, we only consider quasi-static equilibrium constraints. The yellow polytope depicts the equilibrium feasible area for the displayed contact set. If the COM belongs to this area, then there exists a set of contact forces such that the character will remain in its position without accelerating. It is important to observe that in the multi-contact case, this area is not equivalent to the one given by the convex hole of the contact points, as shown by this orthographic view. The intersection of both kinematic and quasi-static constraints results in the purple polytopes, which approximate the set of feasible COM positions for the initial contact set, for the flying face of the right foot, and finally for the end contact set. The intersection of the purple polytopes of consecutive contact faces define the feasible transition set where the COM constraints of both faces are satisfied. This blue polytope defines the set where the right foot can be safely removed without losing balance nor violating kinematic constraints. To generate a motion that safely removes the contact, we choose a transition point in the blue polytope. By convexity, the straight line connecting the initial COM position to this point is a feasible path. A first feasible motion is thus the following one. The character moves to the position and only breaks the contact afterwards. To reach the goal COM position on the left, we find a new transition point where to create a contact. In this example, the previous point already belongs to the transition area, but this is not the case in general. This time, the feasible path is a polyline. The character thus moves forward, creates a contact, and then achieves the motion to reach the goal state. From an aesthetical point of view, the resulting motion lacks dynamism because of the quasi-static constraints. In the paper, we explain how to relax the quasi-static constraints by using the transition points as control points for a Bezier curve such as this one. This allows us to preserve kinematic constraints while generating smoother, more dynamic motions such as this one. In this other example, going from this simple support to this double support configuration is not possible with a quasi-static motion. This is illustrated by the constraints of each contact phase. Here is the constraint polytope for the first phase, and here is the polytope for the second phase. There is no intersection between these polytopes. In such a case, we may decide to relax the quasi-static constraint in such a way that the dynamics will be violated as little as possible. The transition point selected will thus minimize its distance to the dynamic constraints of the first phase while satisfying the kinematic constraints of the second phase. As a result, the kinematic constraints will be preserved. This relaxation allows us to find a reasonable solution instead of simply failing. In this example, we obtain the following smooth center of mass trajectory, which in turn results in the following motion. Because our collision avoidance scheme uses a sampling-based approach, our method will sometimes fail to find a collision-free motion within a given time limit. In such cases, we are not able to determine whether a solution exists for the selected COM trajectory. This is a limitation of our method. In this example, with an increased time limit of 4 seconds of computation, a collision-free motion can eventually be found. The constraint relaxation used by Tupac can lead some of the motions to violate partially the laws of dynamics when the motion is synthesized. For selected examples, we indicate the instance where the dynamics is violated by displaying a red dot, while green dots indicate that the constraints are satisfied. For the chair scenario, the generated motions always satisfy the constraints. Similarly, the walks of HRP2 all satisfy the constraints. For the steep slope scenario, 15% of the times the dynamic constraints are violated because the kinematic constraints imposed to break contact too soon or to create it too late. This is also the case for some of the transitions in the twister scenario. But in this context, most of the violations come from the fact that there is no quasi-static solution that allows a transition. In the climbing scenario, where there is never a quasi-static solution, the success rate decreases significantly as our method reaches its limits.